Yep. Now it should be up. So the question was this one, right? And we said that okay, you have to figure out probability that you start the car given that battery is bad. Yeah, that is what was asked. So how you will do this is, if you look at the figure of this shows conditional independence, right? Now the thing or interdependence among variables. So start is not only dependent on battery but is also dependent on fuel, right? So if that is the case, the only compounding factor that is given here is battery, right? Now you notice that battery and fuel are independent, conditionally independent. And so if that is the case, then you can expand this by just summing up on fuel. Start equals yes, given battery equals bad, and fuel equals empty. Oh, yeah, thanks. And multiplied by probability that fuel equals empty, right? Plus start equals yes, given battery equals bad, and fuel equals full, multiplied by P full. Now turns out that this is 0. How do you get it? So if you look at the question, at the figure, then you see that you have this, a probability that start is no, battery is bad, and if is empty, right? So then what is the probability that S is equal to yes, given battery is bad and F is empty? Just 1 minus that, right? So that becomes 0. And same here, the second part, S is yes, battery is bad and F is full, is this one, right? 1 minus this one, so that becomes 1 minus 0.9, 0.1, right? And then you multiply it with, so this becomes, so this is 0, this becomes 0.1, and P full is 1 minus P empty, right? Which is 0.8, so answer should be 0.08. So we'll update the grade accordingly. Yes?
I think this approach is wrong.
Okay, then we'll update the grade in the other way. Why is it wrong?
Because you are not taking it in the. I forgot the exact reason why we do it like that way, but I know the.
No, if it is a reason, you don't have to memorize.
Yeah, so can I come once again and revise the concept and show it?
Yeah, sure. Sure, you can come to the, so there is a war going on. You fight among yourselves, give me the answer. Don't fight with me. Okay, so that is one reasoning. So now that is the only question that was a little bit confusing. The other ones are pretty easy and we have the answers to them, and those are and there is no ambiguity in those answers. So the others remains the same. Now there are certain papers that are questionable. We have marked 0 on them, so we cannot do anything if you have gotten a 0. That's nothing can be done. So once we are done with that, so today my plan was to discuss reinforcement learning. So did you have any questions regarding the Markov chain discussion we had last time? Or Markov decision process discussion that we had last time? am going to use a very popular set of slides which I didn't develop, but these were developed in in a tutorial in Berkeley. So let's look at this, and this is a basic reinforcement learning introduction. If you are, oh sorry, if you understand, if you have understood Markov decision process, this would be easy. Right? So do you want me to go over Markov decision process again, just as a refresher? So so this was Markov decision process. So MDP is what? It's a model of a game where you take some policies, and these policies are basically sequences or are basically recommendations of actions. So you can model this game or whatever random process you are trying to model. You can model this as a set of states. So here it assumes that the states are fully observable. So which means you have some sensors, you have some ways, either sensors or maybe you have a few sensors, and then you can use a mathematical model to estimate the state. So you have for determining all the parameters of the state. So you know all the parameters of the state. And you also know that at a particular state, if I take an action, I am going to go to another state either deterministically or stochastically. So you know, either you know that for sure you are going to go to that next state, that is deterministic, or you know that 80% of the time if I take this action I am going to go to the next state, and 20% of the time if I take this action I am going to go to some other state. So you know, at least know that. So that is a very big assumption in Markov decision process. So what is that assumption? The assumption is that you have some model of the process. You have a model. You can say something about the process in the future. So if it's stochastic, then you can say that I have a transition probability matrix, and I can multiply it n number of times and say in the future this is what is going to happen. And that I can say. Or if you have a deterministic system, then you can say that okay, if I take this policy, I know that in the future I will be in this state. You know. So since you have a model, that is the assumption of Markov decision process. So what is the model? The model is that. So it's a set of possible world states. Yes. So you know all the states. And a set of possible actions. A. Right? So there are some set of states and there are some set of actions that you can do. And then a real valued reward function. So what is the reward function? If you are in a state S and you take an action A, you get a reward for that state. And then a description T of each action's effect in each state. So what is the effect of an action? You are in a particular state, you take an action, you go to another state. That is the effect of an action. Right? So that is the transition probability. No, not probability. There is a transition description. Right? Now, how do you represent actions? Actions are basically mapping. So mapping means it's a function. So T is basically a function. You take one state, one action, and then you get an output as another state. Right? So that's a function, two-valued function. It takes two inputs and gives one output, the state. Now, since we are talking about reinforcement learning, a key difference between MDP and reinforcement learning is that you don't know T. In MDP, you know T. That means you know the model. But in reinforcement learning, that's why it's called learning. Right? In reinforcement learning, you have to figure out T. You have to learn T. Right? You don't know T. So that's why it is called learning. Reinforcement learning. Otherwise it would be just a Markov decision process. So this T, since you know this T, you know the model. And in reinforcement learning, since you don't know T, you don't know the model. So there can be two ways: deterministic actions, stochastic actions. Deterministic means I already explained that you always go to that state, and stochastic means there is a probability that you might be able to go to that state. Then there are we need to understand certain parameters. So policy pi, what is policy pi? Is a mapping from S to A. So whenever you see mapping, mapping means just a function. From mapping from S to A means it's a function that takes an input in the set S and gives an output of the type A. Right? So policy, if pi is a mapping from S to A, then what does it mean? You can give any state to pi and it will come up with an action. So that is a policy. Now that is not a part of the model. A model can, if you give a state to a model, it will come up with multiple actions, 3 actions. However many arrows are coming out of that state, and it will give those many actions. But a policy is different from a model. Policy says that, okay, which one do you choose out of those 3? That is a policy. Now policy also does not ensure that you will have the same execution all the time. Depends upon your initial state. Right? If you change your initial state, your execution can vary depending upon, and for the same policy, your execution can vary based on your initial state. Right? So policy just recommends that if you are in a particular state, which action do you take? Right? That is a policy. Now this, then, so one is a policy. And then there is an execution of a policy. They call it following a policy. It's not following a policy. And I mean, it is following a policy. But it's the technical term for this is execution of a policy. So execution of a policy means you start from a state and you apply the policy on that state. You go to another state, apply that policy. Again go to the different state, apply the policy, and so on. You continue. So that is an execution of a policy. Right. Now there are 2 very important parameters that we need to understand for reinforcement learning. So 2 parameters are, so expected total reward, okay, yeah, fine. So you need reward. So reward can be expressed as something like this. So M is what? What did we use M for?
Might be optimal value.
M is not optimal. They don't say M.
Number of steps to the goal.
Number of steps is the power of gamma.
The value of that goal.
What?
The value of the terminating state where you are going.
Terminating reward.
So in reward, right? Yeah. So you. No. No, it's not the terminating reward.
What's the question?
Reward that you achieve in the last stage, the end goal.
So no, that is not So there is the cumulative reward. Right? So M is the cumulative reward up until now. So you start from a state. You took a lot of actions, right? You took a lot of actions. Each action gives you some reward, right? So M is the total reward up to that point. Now if you take another step, your M will change. So how will you change your M? So going forward, if you try to calculate the cumulative reward now, then you will discount the M the cumulative reward that you just had the previous state. Right. So that's why it's saying that you have to, so you take next step, you get a new cumulative reward. Now the cumulative reward that you got in the previous state, you discount it by the factor gamma. So that's why gamma is increasing as you go further back. So that is actually, for reinforcement learning, you can have many different ways of having reward. So reward function, you don't have to follow that equation. You can have different types of rewards. You can have objective functions, you can have discounted rewards, you can have expected value of rewards. All those things you can have. So yeah, that is not really very important parameter. But the important parameter is the value function. So value function is what? It's a mapping again from a state. So it takes a state as input and it gives out reward. So represents the expected objective value obtained by following a policy phi from each state in S. So what is it? You have some objective function as a expression, which expression depending upon the reward that you get from each state. Right? So you accumulate that reward in whatever way you can. Maybe you discount, maybe you calculate expected value, whatever way you can. You figure out a objective function. Right? Now objective value which you might want to increase or might want to decrease. What value says is that if I give you a state and I tell you to follow that policy, the policy that you came up with, then it will give you the approximate reward that you will get when you follow that policy. Now in this case, your reward, you have to be very careful because your reward should not be infinite. Because you can follow policy for as long as you want. Right? You can follow your policy for as long as you want. So if you follow your policy and you're just the reward function or the objective value is just summing up all the reward, then that will go to infinity and you cannot evaluate policies. So you have to have an objective function that converges. So you can either do it by discounting or you can do it by limiting time horizon. So however long you take the policy, I will take only the most recent 10 seconds of reward. And so that you fix the time horizon. So value function says that if I give you a state and you start from that state, you take the policy for as long as you want, it gives you the reward. Right? So this means that it's not a one-step reward. So there is no time limit here. You can take the policy for as long as you want, but you will only have that reward. So that is what the value function gives you. Now there is a optimal policy, right? Optimal policy means what? It means that if you take that optimal policy and you start from a state S and you take an optimal policy, then there is no other policy that will give you a better reward. Whether it be maximizing the reward or minimizing the reward, I don't say it. Right? So whatever is your goal, you want to maximize, you want to minimize, doesn't matter. But if you start from that state and if you take the optimal policy, no other policy can do better. So then we have the Bellman equations to calculate the value. Do they discuss the utility values? No. You can take this as utility value also. Anyways. So then it says the Bellman equation we discussed last time, how to calculate value in a recursive way, right? We also said how you can express the optimal value. So these things are mathematical equations. Not going through these again. Right? We already discussed this last time. So now, given this background, let's go and try to see what is reinforcement learning. So they take this example of robot movement. Right? So there are these boxes, and this robot starts at that start point. Now remember, this is a stochastic process. So what they say is that, okay, at any point, it's not move up. So at any point, you try to maintain the direction you are moving in. So if you have arrived to that point by moving up, then your probability of moving up is more. If you have arrived to a particular point by moving right, then your probability of moving right is more. Right? So the move action. So move is an action. Right? If you take that move action, then what is the probability that you will move up, left, right? So they are saying that that is actually wrong. Moving up 8%, no. Maintaining your direction is 80%. And if you want to move left and right, that is 10%. So the thing is, there are two locations. The location 4,3 has a reward of +1, and the location 4,2 has a reward of -1. Right? Now you have to follow, and each step, if you take move action, each move action has a reward of -0.04. Right? Now the thing is, you follow a policy and maximize the reward. So this does not say that you have to reach somewhere. This does not say that. It does not say that you have to reach somewhere. It says that, okay, I will give you a policy, and you move. And let's say what is the best policy that you can come up with. Right? That is what it says. So what's the strategy to achieve maximum reward? We ask the question. What is the strategy to achieve maximum reward? And what if the actions were deterministic? We'll come to that a little bit later. Right? There's another example. We don't need that. So now we have to define a reinforcement learning problem. So what is the learning here? What learning do we have to do? What do we learn from here? What? What is strategy? Do we learn policy? We'll come to that later. We don't even have the T matrix at this point. Right? So that you have to take into account. But okay, let's talk about it a little bit later. So now we have to define what are the states, what are the actions, and what are the rewards. And rewards we know, but we don't know the states and the actions. So which means that we don't even know T at this point. So if we don't even know T, how can we know the policy? Right? That's the question.
The probabilities are the T, right? So
Which one?
The 80%, 10%.
The probabilities are.
It's an MGP problem, right? It's not reinforcement. That given I take an action in some direction, with 80% probability I know the next state. So it's an MGP.
So you are now defining the states, right?
Given state, I mean.
Okay, so there is a disconnect. So the thing is, you can define the states for the computer. You can say that, okay, these states are, each location is a state, moving up is 80%, moving left, right is 10%, these are the stochastic probabilities. you give it. The other thing is to learn it. Yes.
This says that when you take action up, you move up by 80%, and there are 10% chances you move left or right. Same way, if you move left, by 80% of chance you move left, another 10% of chances you move up or to.
Yeah, so that's what, yeah. So 80% of the time you maintain your direction. The other 10% time you can either go left or right. So that is stochastic, it's already given to you. Right? But the thing is, this is, so in reinforcement learning, you don't even know the probabilities. That's the problem. In here, you kind of know the model because you already know that this stochastic probabilities you already know. Yes.
So here these are probabilities of the transitions.
So the way it is
Take
written
next right onto
is
South College Avenue, then
it's
turn
still
right onto East University Drive.
So these are state transition probabilities for now, but the computer does not know it. We know it. Right? We know that if you take a if you came to that state by moving up, then you will maintain the direction 80% of the time. That we know. But the idea of reinforcement learning is that you have to learn those probabilities. Those probabilities will not be given to you. Right? So how do you learn those probabilities? From data, you observe. So there are many different ways to do that. One is by passive learning and the other is active learning. So we will talk about that when we go forward. Let's go with the flow of the slides. So now they are asked. So the question is, okay, I want a policy, right? I want a policy. So if I just tell you that, okay, you go up, then right, you will maximize the goal. If I just tell you that, is that a policy, or is that a particular execution of a policy? It's an execution of a policy, right? It's not telling me it's just telling me a path. Because the other states, I don't know what to do for the other states. A policy has to be a mapping from S cross A to, S to A. Right? So if I pick any state in S, I should get an action. So if I pick a state which is blank, I have no action. So that is not a policy. So policy should tell me, if I start from any of the states, what should I do to maximize my reward? Right? So this is actually not a solution, but this is a solution. This is a solution. This is a policy, because if I give you a state, you know what to do, right? You know, if I maintain the direction from which I came from, so 80% of the time I will go forward. Right? So if I press left here, if I go into this state, if I go into this state, then if I press left, 80% of the time I am going to go here. Now other 10% you won't be able to go anywhere. Right? So basically here, if you press left, you will go 100% of the time here. Or no, actually there can be two different ways. One is you can go 100% of the time there, or 20% time you stay there. You just don't go left, right. So it depends upon what system you are analyzing.
So Professor,
Yes.
so if we start from 3, 1.
3, 1. Where is 3, 1? 3, 1 here. Yes.
Yeah.
What?
So I think the optimal policy should be like we go up, and right. 3, 1.
3, 1 is what? 3, 1.
Like x-axis is 3 and y-axis is 1. The fourth row.
Yes.
And
So see, that is not policy. That is an execution of a policy.
yeah, but this is
So that is optimal execution. Then that would be optimal execution, right? It is not policy. So if you see, why is that a problem? Why can't you go up? So he's saying that, okay, if I start from 3-1, 3-1 that is means this one. Is it showing anything?
No.
So what do I do? What mouse? Just mouse I have to use? Okay. I thought this is high-tech class, so I'm use my finger. So he's saying that, okay, this state, if I start from this state, the optimal policy is going up, and then one right. I'll maximize my reward. Right? So is that the case?
No.
Why not?
There's more probability of going into -1.
Rewards are static right now. If the rewards were diminishing, then the policy would have
No,
automatically.
rewards are diminishing, right?
Rewards are static here.
No, each step you take is minus 0.04.
Since the action
No,
was
minus 0.04 or 0.4?
0.04.
0.04.
It's negative reward is so less that we can take chance of going from that. But if we go from directly from that place, we might receive -1 directly.
Come up, tell it again. Let me understand his solution. Yes, what?
I was saying, suppose if we are going from whatever the location is that, if we go from left and then go up and then go right and exit from +1, and we have negative reward of -0.04, then in that case we can take chance of having negative rewards. But if we go directly up from that place, we can accidentally fall into -1. So we can receive negative reward, which we don't want.
So no, yes. So here you can try to evaluate every possible path, right? You can try to evaluate every possible path and see, okay, which one is the has the best reward. That is one way to do to solve this reinforcement learning problem. Just do dynamic programming and evaluate every possible path. But that is not the point. That is not a policy. That is an execution. That is a single execution of some policy. Which policy I don't know. Right? That is just a single execution of some policy. Now, if I take this policy, so why is this a policy? Why is this a policy?
We are given action for each state.
What?
We are given action for each state.
Not really action. Yes, action, yes, but it says more. It says that, okay, if you are in this state, it's not deterministic that you will take this action. You will take this action 80% of the time. 10% of the time you can go up. Another 10% remain there. Right? So this stochastic nature you have to have it inbuilt. So even if you are saying that, okay, the optimal policy is going up, that is not policy. That is just one execution of some policy. It can be the execution of this optimal policy as well, right?
So the direction of the arrow means 80% probability.
Yes. And why is it 80% probability? How can you come to that point? That 3-1. How will you arrive at that point 3-1? What? You can start from there, or you can start from the other part, or you can start from the top, going down, right? But there is no going down. You cannot go down, so you cannot really start from the top. You have to either start from the extreme left or extreme right, or you have to start from the extreme left, right? So there could have been a policy which would have said that, okay, the arrow is the other way. 80% of the chance you go there. But if 80% of the chance you go forward and go to the left, then what are your options? The only option is the next step. The next step option is to take a -1 reward. That is the only option. On the other hand, if you take this policy, 80% of the time you are taking a -0.04 reward, and 10% of the time you are taking a -0.04 reward on the other part, right? So immediately there is not a -1 reward. So you can see that this going from that state, going right, going left has immediate better rewards. It's immediate. It's not. It's not cumulative. Why it's not cumulative? Because we haven't seen an evaluation of policy yet. We will see. So I don't want to go into that evaluation of policies yet. But if you just see the immediate reward, then this is better than having the other way. You cannot go up. Why can't you go up from that state? You cannot have a policy that says go up. Why can't you have a policy that says go up?
Because if you reach that state, then there's 20% chance that you will go to negative one.
No. I am saying that why can't you have a up arrow instead of a right or left arrow?
That's the boundary.
Yes, but you had up arrow there. That was also the boundary. That is the start state, right? So you have to take some default values there. So that is the start state. So you have to take something. So you can go up. You are assuming that up is the initial action, and it's 80% of the time you take it. So that's why you just go up. There you cannot go up because you cannot reach that state by doing an up operation. You cannot. In there, the last row, the last one, you could have gone up, but if you go up, you take a greater negative reward. So still we cannot say this is optimal. Why? Because we only evaluated one step ahead. In order to really say that this is optimal policy or not, we have to evaluate it n steps and calculate a statistical average of the value. Right? So that we haven't done yet. But we can kind of say one step ahead that this is better. So now the reinforcement learning strategy, what it does is that it looks at data and it comes up with the probabilities 80%, 10%, 10%, and then it runs, or somehow, I don't know whether it runs or not, somehow it has to figure out which policy is best, not just one step ahead. Multiple steps ahead, which policy is going to be the best. So reinforcement learning is a much more difficult problem than Markov decision processes, than solving Markov decision processes. Here you can evaluate policy. You can definitely evaluate policy. You can say that this is optimal policy. How? Because this is not really reinforcement learning. This is NDP, because you know the probabilities. So since you know the probabilities, you can get a Markov chain. You can make a Markov chain out of this, right? And you can multiply the transition matrices n number of times, calculate average values, and you will figure out what is the average time spent in each state, right? Over infinitely long simulation. And you can figure out the reward, average reward for each policy. That is possible. But if you don't know the stochastic probabilities, it is not possible. So reinforcement learning tries to understand those probabilities. So that is one big difference. So now let's say that, okay, what if you increase the reward for each step? So this shows the different optimum policy for different negative rewards for steps. So it says, okay, what if you increase the reward for each step, right? And make it -2. How it changes? How does the optimal policy change? So if you see that a lot of arrows went towards -1. Previously, you are avoiding -1, right? You are avoiding -1. Even if you are there, you didn't go up. Or even if you are here, you didn't go right. You went up. Why? Because you tried to avoid -1. But if each step, taking each step as a greater negative reward, more negative reward, then you would try to go towards +1 in the shortest path possible, right? Because now each step you take, you have more and more negative reward. So you would prefer shorter paths. So if you do that, if you see that this arrow changed to the right, that doesn't mean you always take the right step. It means that 80% time you take the right step, but 10% of the time you could have taken up also. So a lot of arrows, they switch, and see this arrow, this one, the one here, this one previously it was right, and we said why didn't it take up? It could have taken up, but it could have gotten a bigger negative reward, right? So that's why we took right. But now it turns out that taking extra steps is a problem, because now each step has a -2 reward instead of -0.04. So that's why it directly goes up. Right? So if I change the reward in each step, optimal policy changes. Now if I make it -0.1, which is still greater than the previous rewards, but little less, right? Little less than the last one. So -0.04 instead of that we have -0.1. So you say lesser number of arrows go towards -1, but they do go. So for example, this one changes. This one changes to, no, this did not change. Oh, this one changes to down. Why does it change to down though? Oh no, sorry. That's the wrong one. Yeah. So if you change from -2 to -1, if you choose from -2 to -0.1, then again you see the same trend, that it tries to take a roundabout path, trying to avoid -1. Right? So previously here these ones were taking -1 reward because they knew that each step will cost -2. But now you are not taking -1 reward, because now you see that each step costs less. Right? It costs less. So you can avoid -1. But still, if you go further from -1, if you look at this state which is further from -1, it still goes affinity towards it. Right? It was here, it further from -1, it was, but still going towards -1. But now if you have -0.01, it still stays here, this particular state. So why it stays here? It still stays towards the right. Why does it still stay towards the right? Because although you have reduced the reward for each step, the cost for each step, basically negative reward. Although you have reduced from -2 to -0.1, still it might be beneficial to, it might not be beneficial to take a roundabout way, which was taken by the optimal policy. Because in the optimal policy you had a reward of -0.04, which was much lesser. So you could have taken more roundabout approach towards +1. So it shows different ways of, if you change the reward, what kind of policies you want to take. So from this, what I want you to take is the distinction between policy and policy execution. This is a very, very important distinction you need to make when you are talking about reinforcement learning. This is a stochastic environment. So showing that you have a right arrow doesn't mean you always go right. That you have to understand. It's a policy to go right. In that state, it's a policy that I'll go right. But do you really go right? May not be, because it depends upon the stochastic nature. So 80% of the time you go right, but 10% you may not. So this distinction is very important. And also you understand the complexity in coming up with the optimal policy. The complexity, why is it complex? Because just the shortest path towards +1 may not be the best path. And also +1 may not be the ultimate goal. Right? Policy is policy evaluation is over infinite time. So it's not that you have to reach +1 and stop there. Right? You have to continue. So how do you continue? So it can also depend upon how you reach +1. Right? If you reach +1 from, let's say, -1, if you reach +1 from -1, then what can be the next step? What?
Go out, come back again.
Go out how? How will you go out? Do you go back to -1? Is there a possibility to going back to -1? You cannot, because you cannot take down step. The only thing that you can take is a left. But what if you arrived at +1 from the left? The immediate next step could be -1. You will take more negative reward or cost. Negative reward, let's call it cost. Right? And positive reward is reward. So your reward that you get depends upon how you reach +1. So that's why you cannot just stop at +1 and say that, okay, that is my reward. You have to continue your policy to infinite time. And in the limit, say which policy gives me better. Yes.
In this game, the game actually ends if you reach either the +1 or the -1. That's why the arrows stay away from them completely here, because they never want to reach.
Yeah, because you basically for a different reason. Because when you reach those, the reward gets to 0. The reward gets very close to 0. So we'll talk about that. We'll talk about that a little bit later. That's why you stop, because the reward is 0. So you don't really stop. Basically, it's same as if you restarted. Right? So you may not stop, but whatever you did after reaching +1 or -1 doesn't matter. Sorry, before reaching, whatever you did before reaching +1 and -1 doesn't matter. So you may still continue, but your analysis stops there. So we'll talk about that later. So then they talk about, okay, we can model this scenario using MDP. This part we have already talked about. But the thing is, we don't know the probabilities, we don't know the transitions, we don't know the policies. So we have to learn. So that is what they are saying is a reinforcement learning problem. Now, so they are saying the transitions and rewards are usually not available. So you have to learn the rewards, you have to learn the transitions. So for example, if you think about an Atari game, for the first time you are playing it, you don't know when the monster is going to come and the prince is going to destroy that monster. Right? Which path do you take? Or which policy do you take? Do you go with the sword like this, or do you go with the sword like this? Right? You don't know what is the effect, because this is the first time you are taking you're playing that game. Right? So so you have to somehow learn that, do I do this or do I do this? And what is the reward for doing this, and what is the reward for doing this? You have to learn. Right? So what is one way of learning? Maybe if you go for the throat of that monster, its life reduces by 60%. But if you go for the hand, its life reduces by 20%. So you learn that. You do it and you learn it. That is my reward for this action. And then you remember it. Right, next time. So you first do it, you get the reward, and you remember. So that is one specific way of reinforcement learning. That is execution, collecting data, observing the system in a passive manner for a long time, and then learning the rewards. Right? So just do it. That is one way of doing reinforcement learning. But the point is that transitions rewards are not given. So you have to take, you have to figure out. Now the question is, okay, if the transitions and rewards are not given, what policy do you take? Because you have to start playing the game. Even to observe what is the reward, what is the transition, you have to take some policy, right? You have to move forward or move backward or do something. So what is that initial policy? Right? How do you know what is the initial policy? It's a default value you can take. Because every time you start up or every time you start right, that you can take. Now once you have taken a default policy and you are executing the game, you understand that, okay, if I do this, this is my reward. If I take this action, I go to this different state. So you learn the transitions, right? Once you learn the transitions, since you now know more knowledge about the game, how do you change your policy? Or does your policy remain the same? Your policy might change, knowing the transition probabilities and knowing the state transition matrix, right? Your policy might change. So how do you change that policy? What do you do? What changes do you do to that policy? And how do you know what change to make? That is another question that reinforcement learning asks or gets answer for. So not only the transition probabilities, not only the state transitions, you also have to tell me, first you take an initial policy and then you have to tell me how to change the policy. So that is also one thing that the reinforcement learning does, learns how to change the policy. And then once you have fixed or once you have updated your policy, right? Once you have updated your policy, for a given policy, there can be many different executions of the policy, right? Depending upon start state. So how to explore those different possibilities of the same policy that you came up with? So it cannot be decoupled. Exploration of a policy cannot be decoupled from changing the policy. And if it is decoupled, then it will take a long time to learn. So what you have to do is you have to explore and change at the same time. So maybe in a time sequential manner, you first explore, then immediately change, then explore, then change. So your exploration should also mutate. Your exploration technique should also mutate based on how your policy changes. So it's a very complex problem, the reinforcement learning. And there are a lot of things to do. So you are at the same time you are doing three things. One, you are trying to understand the probabilities, you are trying to understand the transitions, right? So you are learning the T parameter and you are learning the probability parameters, and often you are also learning the reward. Right? You might choose to give different rewards to different actions based on what is happening. Right? So you want to fix the rewards, you want to fix the transition matrix, you want to fix the transition probabilities or learn them. In addition, you first have to choose an initial policy and you have to learn how to change the policy. Right? That is one thing. And then the fifth thing is that, or the third thing is that once you change the policy, how do you use the new policy to explore all the possibilities? And once you explore one possibility and you understand that you need to change the policy and you go and change the policy, you have to change your exploration technique. So doing it in a brute force manner is almost impossible. Because if you go one way, it changes, then the way that you went is invalid, you have to go back and go the other way. So doing it in a brute force manner is extremely difficult. That's why you have so many algorithms. Right? So there are different ways to do it. Computing, this we have already understood. And value functions we have talked about, the Bellman equation and all that. And optimal value functions and all that. So now solving a reinforcement learning problem. So you can do dynamic programming, which is basically exploring all possible possibilities, but it is in a structured way. In a structured way. Or you can have Monte Carlo methods, is a randomized simulation. Right? What is anybody knows Monte Carlo method? Yeah, so some people, yeah. So basically randomized simulation. You take a sample and you assume a distribution, and you pick a neighborhood, and in that neighborhood you pick some samples randomly and then simulate them. Right? So you can do that. And then there is another called temporal difference learning. We will talk about that a little bit later. Right? But all these learnings can be classified into two broad categories, which they have not listed. Why not? They have not listed active and passive learning, the difference. Okay, anyways, I will discuss those. So let's stop here. There's a lot to take in. Let's stop here, and from next time we'll start with active and passive learning, and we'll look at some of the techniques, so Monte Carlo, time difference, some of the techniques to build reinforcement learning. And then we will talk about an example that uses reinforcement learning in recommendation systems. So I will assign you a paper that you have to do.
Passing out.